Good morning everybody. Myself Suman working as a lecturer in CE department at BHS BIT Laragaga. Today my topic of our lecture is windowing and clipping. Basically this topic is concerned with the display of the scene on the output devices. There are various topics that I will cover through. First of all, the two-dimensional viewing, how a scene is to be mapped onto the output device, whether that device may be a LCD screen, that may be a LED screen. The dimensions of the display device doesn't matter, because we are mapping from the world coordinate to the viewport transformations by a normalization. Then the next is clipping. Clipping is a procedure for selecting those portions of the scene that are either inside or outside the scene. The inside portions of the scene will be clipped in, so that they can be displayed on the output device, and the outside portions of the scene are may be clipped out of the scene, so that they may not be displayed on the output device. There are various types of clipping operations. Suppose such as point clipping is there, line clipping is there, and polygon clipping, text clipping, exterior, and the blanking, one of the topic that is under the clipping I will cover. So till now in the previous lectures we have created various primitives using the scan conversion of a line, of a point, of a polygon, curves, circles, ellipses, etc. Then after that in the next lectures we have transformed those objects, so that we can change the size, orientations, positions, and we can create the double copy, mirror image of those objects. So till now we have just created all those objects, we have just prepared the objects for the scene. In this lecture, I will explain the formal mechanisms for displaying the views of a picture on an output device. Typically, the graphics packages allows a user to specify which part of a defined picture is to be displayed, and on which portion of the on the display device where that part is to be displayed. There are two things. First is the defined picture. From that defined picture, which part will be displayed, and on the display device where that part is to be displayed. So any convenient Cartesian coordinate system, referred to as the world coordinate reference frame, can be used to define the picture. For a two-dimensional picture, the view is selected by specifying a sub area of the total picture area. For a two-dimensional picture, suppose we are viewing the whole scene, but we are not to project the whole scene in our camera, in our window. We will select the sub area of that portion of that overall scene, so that we can display the required scene on the display device. So user can select a single area for display, or several areas can be selected for simultaneous display, or for an animated panning sequence across a scene. Suppose sometimes the scene is varying from one position to another and the camera is still, and sometimes another vice versa of this occurs. The scene is still, we are moving around the scene, we are moving our window, we are moving our camera around the scene. That effect is called panning effect. So user can select the single area for display, or the several areas could be selected for the simultaneous display on the single screen. The picture parts within the selected areas are then mapped onto the specified regions of the display screen on the device coordinates. When the multiple view areas are selected, then there is a question how they will be placed on the display locations. These areas can be placed in the separate display locations, or some area could be inserted into the another larger display areas, that is a nesting of the scenes into one another. Then the transformations from world coordinate to the device coordinates involves the translation. Translation means we are changing the position of scene from one location to another. Rotation, we can change the orientation of the scene. Scaling operation, we can change the size of the object, as well as the procedures for deleting those portions of the picture that are outside the limits of the selected display area. Suppose for example there are two monitors, this is workstation 1 viewport, here this is the scene to be displayed, and here this is the scene to be displayed. Both these scenes are to be selected for the next display normalized space, that is the display device. Both these scenes are to be placed into the single viewport. So, simultaneous simultaneous scenes can be selected for display onto a single display device. Next, the viewing pipeline. Before explaining in detail, I just here quote some definitions. What is a window? A world coordinate area selected for display. A world coordinate area selected for display, which will define what is to be viewed. What is to be viewed? We are just free for the free for selecting the view. We are just free for selecting the view. So, window will define you what is to be viewed, and the viewport is an area on a display device to which a window is to be mapped. Viewport is just related to the display device to which a window, means to which that scene is to be mapped. Viewport defines where that scene is to be displayed. Window will define what is to be displayed, what is to be viewed by the camera, by the any other device that is used for viewing, and viewport will define where that portion, where that scene, where that display is to be displayed on the device. So, viewing transformation is what? That is the mapping of a part of world coordinate scene. Mapping of a part of world coordinate scene, that is what is to be viewed, what has been viewed in the world coordinate. From that we will select the scene, and that is to be mapped onto the device coordinate. This is called viewing transformation. Your window could be a rectangle to have any orientation. That window could be a rectangle to have any orientation. Here the two dimensional viewing. First of all, this is the world coordinate, the overall, suppose this is the hilly area for example. Overall scene is there, but according to the window size we have selected this portion. This window size is specified in the two dimensional. So, here is the x coordinate from the x w minimum, the window x coordinate minimum to window x coordinate maximum. Similarly for the y coordinates, and this view is to be mapped onto the device by using viewport. That portion that is selected for the viewing is to be displayed on the viewport on the device by using the viewport dimensions. This is the viewing pipeline. There are a number of steps how your scene, natural scene is to be transformed, is to be displayed onto the device using the viewport device coordinates. These are the various steps I will explain. So, some graphics packages that provide window and viewport operations allow only standard rectangles. Generally we use the standard rectangles for viewport and window, but a more general approach is to be allow the rectangular window to have any orientation. The window should be rectangular in size, but orientation is independent. In this case we carry out the viewing transformation in several steps as shown in the last figure. The first step is we construct the scene in world coordinates using the output primitives and attributes. Output primitives means the points, lines, curves, etc. We have to construct the scene in world coordinates using all those output primitives and their attributes. Then the next step, to obtain a particular orientation for the window, we can set up a two-dimensional viewing coordinate system in the world coordinate plane and define a window in the view coordinate system, and define a, suppose for in the first step we have construct the world coordinate scene. In the second step we will convert the world coordinate to the viewing coordinates. Then the viewing coordinate reference frame is used to provide a method for setting up arbitrary orientations for rectangular windows. Now, the viewing coordinate reference frame could be used for setting up arbitrary orientation. The orientation is flexible, any kind of orientation we can use for the rectangular window. Once the viewing reference frame is established, we can transform the descriptions in world coordinates to viewing coordinates. We then define a viewport in the normalized coordinates. In normalized means in the range from 0 to 1, and map the viewing coordinate description of the scene to normalized coordinate. This normalized coordinate description is used so that the scene is independent of the device. There are various kinds of devices. Number of dimensions are there, number of height and we can say number of pixels, number of vertical and horizontal lines may be different for each and every device. So, the scene may not be changed according to the dimensions. Scene must be independent of the display device. For that we use the normalization. At the final step, all the parts of the picture that lie outside the viewport are clipped. That is, the clipping operation will be performed and the contents of the viewports are transferred to the device coordinate. These are the steps which are followed in the viewing pipeline. In the next figure, that illustrates a rotated viewing coordinate reference frame and the mapping to normalized coordinate. Here the window is rectangular, but the orientation is different. So, we have just rotated this so that it becomes to the normalized device coordinate. So, by changing the position of the viewport, we can view the objects at different positions on the display area of an output device. Suppose we want to display the scene. At this portion we can change the size of the, we can change the position of the viewport. Also, by varying the size of the viewport, here we are saying that we can change the position of the viewport, we can change the size of the viewport. By changing the size of the viewport, we can change the size and proportions of the displayed objects. If we want to enlarge, we can enlarge. If we want to reduce the display objects, we can reduce the display objects by changing the size of the viewport. We achieve the zooming effects by successively mapping different sized windows on a fixed size viewport. The viewport will remain fixed size, but the windows that are to be mapped onto the viewport, they may be changed, they may be different size. As the windows are made smaller, we zoom in some part of a scene to view details that are not shown with the larger windows. Similarly, if we want to zoom out something, more overview is obtained by zooming out from a section of a scene with successively larger windows. The last is panning effects are produced by moving a fixed size window across the various objects in the scene. This is the animation effect. These are the various effects. In brief, I have explained zooming effect, panning effect, and the device independent, the normalized coordinates will make the view independent of the device. The viewing coordinate reference frame, this is used for specifying the world coordinate window. The window to viewport coordinate transformation. Till now we have, once the object descriptions have been transferred to the viewing reference frame, we choose the window extent in the viewing coordinates and select the viewport limits in the normalized coordinates. Once the object descriptions have been transferred to the viewing reference frame, we choose the window extent in the viewing coordinates and select the viewport limits in the normalized coordinates. Object descriptions are then transferred to the normalized device coordinates. We do this by using the transformation that maintains the same relative displacement of the objects in the normalized space as they had in the viewing coordinates. I will explain it with the help of equations. If a coordinate position is at the center of the viewing window, for example, it will be displayed at the center of the viewport also. The position, the relative displacement from the boundary of the viewport will be same as in the window, that is the defining objects at the time of defining the objects, at the time of defining the scene. The displacement will not change. For example, if this point xw window, in the window this point xw and yw is at this displacement. This displacement is maintained in the viewport also by same distance. So, world coordinate, the clipping window is mapped onto a, this is the window that is to be mapped onto a viewport, world coordinate, and the viewport coordinates, viewing world has its own coordinates. That may be a uniform, non-uniform scaling of the world coordinates. It is not necessary that the window size and the viewport size will remain same, or the dimensions of the window and the viewport will remain same. That there may be a non-uniform scaling. The size may change, but the scene is to be mapped accordingly. If this corner is from this, whatever the displacement is, that proportion is to be maintained in the mapping also. So, the previous figure illustrates the window to viewport mapping. A point at the position xw is to be mapped onto the xv yv in the viewport with the same displacement in the associated viewport to maintain the same relative displacement in the viewport as in the window. What we require is that this is the equation, that xv, that point minus this distance upon the total viewport size equal to the window point minus this distance upon the total window size. They should be in proportion, they should be equally proportional to each other. Similar is for the y direction, that is y axis, yv, this point yv minus this thing, this distance upon the total y direction, that is the vertical size of the viewport, should be proportionally equal to the this distance upon the vertical distance of the window should be proportionally equal to each other. So, solving for these expressions for the viewport position xv and yv, how we can, what we have, xv is equals to y xv minimum plus the window that is the window proportion into sx. Sx is what? Scaling factor in the x direction. Similar is the for the yv. This is the equation we will get after multiplying and solving for the expressions, where the scaling factors are xv max, that is the viewport size in the x direction, upon window size in the x direction, and scaling factor in the y direction, that is viewport size in the y direction upon window size in the y direction. Above equations can also be derived with a set of transformations that converts the window area into the viewport area. This conversion is performed with the following sequence of transformations. First of all, we perform a scaling transformation using a fixed point position of the xw to yw. We will scale the size of the window according to the size of the viewport. So, that we will scale the size of the window with the fixed point position according to the fixed point position, that is xw yw. We will scale the window area so that it will be equal to it will be equal or it will be in proportion to the size of the viewport. After that, we will translate the scaled window area to position of the viewport. These are the two transformations combined. In the combined form, it will become like this. We are just translating first the xw minimum and the yw minimum, and so that it coincides with the region of the, so it will become the same as the viewport. Then we will scale it by sx and sy factors we have defined in the last slide, and after that we will translate back to the back by the position of viewport. This is the window to viewport coordinate transformation. So, in case of normalization and viewport transformation, there are two approaches. First approach is normalization and window to viewport transformations are combined into one operation. Viewport range can be in 0 1 into 0 1, and clipping takes place in 0 1 into 0 1, then the viewport is then mapped to the display device. The second approach is normalization and clipping takes place before viewport transformation. Viewport coordinates are specified in the screen coordinates. There are two approaches. This is the brief after all the explanation. A screen is made up of collection of objects in the world coordinates, right? When we display a scene, only those objects within a particular window are displayed according to the window size. Not whole the scene will be displayed, only the particular objects, only those objects that are in the particular window size are displayed on the display device. Because drawing things to display takes time, we clip everything outside the window. Whatever the scene, whatever the objects will remain outside the window, that will be clipped outside the window, that will not be displayed on the screen. The next is now the clipping. This is next portion related to the display of the scene on the display devices, on the output devices. So, generally any procedure, what is clipping? Any procedure that identifies those portions of a picture that are either inside or outside of a specified region of the space is referred to as the clipping algorithm, or simply we can say clipping. The region against which an object is to be clipped is called a clip window. The region against which, suppose that may be the size of the window, that may be the size of the viewport, against which we are specifying the portions of the picture that are either outside or inside. There are various applications of clipping. Extracting the parts of a defined scene for viewing means the scene is defined in the world coordinate. After definition of that scene is to be displayed on the in the viewport. For viewing those defined scene, we are to extract the parts of the scene which are to be displayed or which are to be clipped. Identifying the visible surfaces in the 3-dimensional views, that will be discussed in your next lecture, 3D graphics. Then anti-aliasing the line segments or object boundaries. When we display the line segments or some other object, their boundaries or their some portions will be aliased. So, by use of clipping, we can anti-alias those segments. Aliasing is what? The unequal brightness may be there. There are number of factors which we can make sure that will not happen in our display by use of clipping. So, creating objects using solid modeling procedures and displaying a multi-window environment. On a single window, suppose sometimes what we do in our daily routine when we are on a PC, when we are working on a PC, there are number of windows that are to be simultaneously opened on our screen. Suppose there are number of Internet Explorer screens, there may be number of Word, MS Office screens. The portions, those multi-window environment will be displayed only with the help of clipping. In that, the active window is displayed completely and the inactive windows which are behind the main active window, the portions which are to be displayed of the inactive window, that will be exterior to the active window only. In that, exterior clipping is used, and drawing and painting operations that allows parts of a picture to be selected for copying, moving, erasing or duplicating. These are the various applications of clipping. So, in the following section we will consider the algorithms for clipping the following primitives. First of all, the point clipping, because this is the basic primitive that is used in each and every next primitive to be scan converted. With the point clipping we can draw a line, with the point we can draw a line, area, curve, text and so on. So, point clipping is there. Line clipping, that is a straight line segment, how they can be clipped if they are out of the viewport. Then the area clipping, in the area clipping we will cover the polygons, various kinds of polygons can be there. Then the curve clipping is there. Then next is the text clipping. Text means the written characters. There are various strategies for that. Then first of all, point clipping is there. Point clipping is basically very easy. There is a point xy, suppose there is a point xy that is not clipped if these are the following inequalities are satisfied. Means xy should be within the limit of, x should be within the limit of xw minimum and xw maximum. It should be within these limit. If the point is in within this limit x and the y also, in the vertical direction also, the window size, if the point is within this region, that point is not clipped, otherwise the point will be clipped. So, point is not clipped if these two inequalities, these are called inequalities because these are not equalities, these are inequalities, are satisfied, the point is not clipped. In this example we can see the points which are clipped, that will be P4, P2, like P2, P8 and P10, P7. All these points will be clipped because they are outside of the window size. Then the points which within the window are not clipped, like P5, P1 and P9. These are the points which will not be clipped because they are within the size of the window. Next is the line clipping. This is somewhat harder than the point clipping. So, we will examine the endpoints of each line to see if they are in the window or not. For line is what? Line is defined as a collection of two endpoints. Line can be defined as a line can be defined by specifying two endpoints of the line. So, we will examine only those two endpoints of each line to see if they are in window or not. There are three ways, there are three situations which can occur. Both endpoints may be inside the window, both endpoints may be inside the window. देखो, this is the window and both endpoints are within the window. If this is the situation, we will not clip to the line. The solution is do not clip. The whole line will be remained in the display. One endpoint is inside the window and one endpoint is outside the window, like this. One endpoint is inside, one is outside, one is inside, outside, inside and outside. In this situation, the whole line is not within the window. So, we are must clipping these types of lines. How we will clip, that is the portion of next slides. So, the third situation is both endpoints outside the window, like this. Both the endpoints are outside the window. In this cases, there are two options. If the both endpoints, like in this example, the two endpoints are out of the window and the whole line is also outside the window. This line will be completely outside the window, will be clipped off. Then this line is, the two endpoints are out of the window, but the whole line is not outside the window. In this case, we are to clip the line by finding their intersection with the window boundaries. That will be explained later on. So, first line clipping, that is brute force line clipping technology method. Brute force line clipping can be performed as follows. First is, don't clip the lines with both endpoints within the window. Obviously, don't clip the lines with both endpoints within the window. If the line having both the endpoints in the window, we need not to clip those portions. That will be displayed directly in the screen. For lines with one endpoint inside and one endpoint outside, we are to calculate like this: one endpoint inside, one endpoint outside. We are to calculate the intersection points with the boundary and clip from that point. Clip from this point out. The portion which is outside of this intersection, that will be clipped out and this portion will be clipped in. This intersection can be find out with the by use of equation of line, that is y equals to mx plus b. The last situation, that is for lines with both the endpoints outside the window, both endpoints outside the window, this and this endpoint outside, this endpoint outside. What we are to do, test the line for intersection with all the boundaries and clip appropriately. For these types of lines which are having both the endpoints outside the screen, outside the window, we are to find the intersections with all of the boundaries, whether that is the left, right, top and bottom boundary. With all the boundaries, we are to find the intersection of the line so that we can clip appropriately. So, however, calculating these types of line intersection computationally will be expensive, because a scene can contain so many lines. The brute force approach to clipping will become very much slow. So, the next clipping algorithm that is superior, that is efficient, and this is the oldest and most popular procedure for line clipping. The key advantage behind this algorithm is that it vastly reduces the calculations, the number of line intersections that must be calculated in the case of brute force. So, there is no time consuming. This is a direct method. In this Cohen-Sutherland line clipping algorithm, world space is divided into the regions based on the window boundaries. Each region has a unique 4-bit region code. Region codes indicates the position of the regions with respect to the window. A 4-digit binary code assigned to every line endpoint in a picture, numbering the bit positions in the region code as 1 through 4 from the right to left. I will explain. The whole window is divided into the 9 regions. This is the window interior, this is the window right side, this is the window left side, this is the window's top, and this is the window bottom. These are the this window, whole world space is divided into 9 regions, and each region is assigned a 4-bit region code. The region codes will indicate the position of the regions, like 0 0 0 0. The first bit is left, for the left position, right, then bottom, and then top. So, if there is a 1 in any position, it means the region is in the right of that, in any position, that region is that line and point is in the right side of the region. If this suppose 0 1 0 0, a 1 in this second position, it means this is the right of the window A.